All right, this presentation is about a new product that we're releasing called AmpWash solder paste. It's part of our process amplifying series of solder pastes. First, we'll talk about highlights and the parameters for the solder paste and standard data of the standard tests that we run. And we'll go into some detail on performance data. So we've done extensive print, reflow, and void testing with this material, and we're quite excited about it. And then I've got some information on high reliability alloys that are available with this solder paste, including SO100CV, LFC2, and TempSafe B37. And at the end, I'll have a summary of all of this, and then we'll have time for questions, as Jeremy mentioned. So here's an overview and some technical data around this solder paste. First of all, the solder paste was designed primarily to reduce voiding potential as compared to other water-soluble lead-free solder pastes on the market. That is a problem that I run into quite often, especially with all manner of water-soluble solder paste, because they have a tendency to absorb moisture out of the air. And then when reflowed, that moisture becomes gas, obviously, and sometimes can get trapped in the solder joint, creating higher voiding levels as compared to no cleans. The solder paste was also designed to have excellent printability and excellent activity, so it can wet difficult surfaces. And the reflow performance overall is quite good with this product. It provides excellent wetting, very low solder balling, very low graping potential. And the other thing about this solder paste that we were targeting when we formulated it was to provide excellent washability, even under tight gaps, like with low standoff components. And I've got some data to share on that, but there will also be a paper presented at SMT International in about 2 weeks, specifically regarding different types of cleaning testing and then SIR data that was run on this solder paste as compared to an industry standard solder paste. And then this is, of course, available with a variety of solder alloys, including TempSafe B37, which is from Nihon Superior. That particular alloy is a low melting alloy that has improved rock shop results over traditional tin bismuth alloys that have either 57% or 58% bismuth. So here's the current alloy availability for this product. So obviously SAC 305 is a standard that we make all of our solder paste to work well with. Then there's SO100C, SO100CV, which is a modified version of SO100C with a little bismuth added to it. Then LFC2 is a high reliability alloy that's designed for automotive applications. And then TempSafe B37, like I mentioned just a minute ago, is a lower melting alloy that melts between 139 and 174 C. And then, of course, there's anti-tombstoning mixtures available. I'm not going to go into detail on that during this webinar, but we've got previous presentations about tombstoning. In fact, I think the last one we did was about tombstoning, where we published a paper last year's SMT International about that. And so if you're interested in that, that's available on our website. Here are the standard print parameters that are listed in the TDS. I'm not going to go through these in detail, but just be aware that this is pretty standard. It's designed to work in a wide range of reflow or print conditions and a wide range of reflow conditions. And so the parameter guidelines here are fairly wide to accommodate a variety of different processes. Here are the generic reflow profile guidelines that we've established for this solder paste. Again, these are very standard and very similar to our other products. Here's the IPC testing data to go along with this solder paste. So here's the J standard 004C flux classification. It's classified as an ORH1, so it is high activity and does contain halides. It also contains halogen activators. So it's a highly active solder paste. And it definitely helps. That helps to improve wetting, especially on difficult surfaces. But in this case, special materials were chosen in order to improve voiding potential. Here's the copper mirror test. So that's a droplet of flux on the copper mirror. And then we look for penetration of that thin layer of copper on the copper mirror. And in this case, full penetration occurs. So that definitely contributes to the high activity classification. Here's the IPC SIR test data and the ECM test data that passes both of those tests. Of course, after washing off the flux residue. When tested, part of the paper that we're presenting at SMTA International this year, we actually tested SIR data on this particular product without washing it off. And it definitely failed in that test, but it was still interesting. The resistance values are relatively high. Anyway, so you definitely have to wash this material off. It is corrosive and conductive and will create electrochemical migration. Here's the J standard 005 solder paste data. This is all just standard passing data, except solder balling is preferred in this particular test. Here's a picture of the cold slump from IPC test method 35, excuse me. And here's a picture of the hot slump from that same test. And here's a summary of the slump data. It passes slump without any issue. Here's an initial picture of the solder balling test. Here's after initial reflow at 245C, almost no solder balls in that flux ring. And then here's a picture of the same test after it was stored for 4 hours at 50% relative humidity and then reflowed. Again, preferred results in these two tests. Now here's performance data that we generate based on internal testing in our laboratory. Here's a tack force change over time. So we have tack force on the y-axis here and storage time in hours on the x-axis. We run this test over a 72-hour period, and we test tack force coupons every day for 3 days. So amp wash is the blue line, and it maintains its tack over 48 hours, which is much improved performance over the current product. Current technology lost tack within the first 24 hours, as you can see here. Here's stencil life in a print and pause test over 8 hours. So we kind of combine stencil life and print and pause together in this one test. So you've got transfer efficiency through a 0.50 area ratio aperture. It's actually a 0.4 millimeter pitch BGA pattern that we're measuring here. And you can see the blue line is amp wash and the red line is the current technology paste. The current technology paste is very stable in this test. It holds its transfer efficiency over 8 hours with pauses of 1, 2, and 4 hours. Whereas amp wash doesn't hold up to the 4-hour pause. As you can see, between hours 4 and 8, it drops off transfer efficiency pretty significantly, but it definitely handles 1 and 2 hour long pauses without any issue. So the printing was good through 4 hours with pauses up to 2 hours, which is more than adequate for any kind of application in the industry. We make these solder pastes to these types of tests within our lab in order to try to make them fail, to be honest. So these tests are not representative of normal practice out in the world. Instead, these are designed in order to try to figure out the strengths and weaknesses of the solder paste. So this particular solder paste amp wash will run fine on your printer if you're not pausing for more than 2 hours, and then you're also adding to it normally as normal production would dictate. Here's wetting data for amp wash versus the current solder paste. The golden colored bars for ENIG surface finish and the dark red bars for OSP. You can see the wetting on OSP is almost identical on these two. Very low wetting or spread percentage there in the low 20s, which is pretty typical for OSP. On ENIG, amp wash and the current solder paste are definitely a little bit different. The current solder paste actually wets and spreads very far on ENIG, whereas amp wash spreads a little over 60%, which is pretty typical of a lot of different solder pastes. Both are more than adequate for wetting both OSP and ENIG surface finishes. Here's the big kicker with amp wash. This is the main thing it was designed to do. It was designed to reduce voiding levels from the current solder paste here on the left, had void areas ranging from, say, 25 to 35% roughly in both ramp to spike profiles, and ramp soak spike profiles. And that's pretty high. That void area is beyond normally accepted limits for most of our customers, which 25 is a pretty widely accepted number on these types of components. Sometimes we hear about lower numbers as low as say 15 or 10% void area. Well, the current technology, water soluble lead-free pastes are usually not able to handle that. Whereas Amp Wash gives you voiding down below 5% void area on the same test board with those same QFN components. So we're considering that to be an ultra low voiding solder paste. In fact, I've run some testing in the field with this product, and I've seen similar void results where it's actually outperforming some no clean lead-free solder pastes in the market, which was shocking to me, but it's good news. We really like that fact about this solder paste. So here's a little excerpt of data from the paper that I've been talking about that'll be presented here in about 2 weeks at SMT International. So we partnered up with Magnalytics, who ran SIR testing underneath low standoff components. So these are Magnalytics test boards that have QFNs, BGAs, and there's a variety of chip components and a QFP as well. And the SIR comb patterns are running kind of in between and underneath these components. And so the current technology solder paste is on the left, and that was run with a linear profile and just DI water cleaning, no chemicals were used. And you can see there's 4 different color lines here for SIR. Those are the 4 different regions on the board that are being tested, 4 different comb patterns. And so a couple of those comb patterns actually were below 10 to the 8th ohms here, which is the 8 on the y-axis, which means they technically would fail here at the beginning. And then this yellow band is kind of the cautionary zone between 10 to the 8th and 10 to the 9th ohms in this test. So the current solder paste had pretty low SR numbers even after cleaning, whereas the new solder paste, Amp Wash, and under the same conditions, all the resistance values were above 10 to the 9th and much higher than that. So quite a bit better SR results after cleaning under low standoff components. And that was one of the other major goals for this product, to enable improved cleaning, especially in tight gaps. So now I'm going to switch gears and talk about high reliability solder alloys that are available with this solder paste. So here's some data on SN100CV, which is tin, copper, nickel, and bismuth, shown on the right. And then SAC305 is shown on the left on this chart. And this is a tensile strength chart. The blue bar is as cast or freshly prepared ingots. And then the red bars are aged 500 hours at 150 C. You can see SAC305 loses tensile strength as you age it, whereas SN100CV does not. And that's because SAC305 depends upon solid particles, intermetallics of silver, copper in that alloy that get coarser over time. They grow in size, they agglomerate together, and that coarsening effect makes it lose tensile strength. Whereas SN100CV has an amount of bismuth chosen to remain in solid solution, and it's uniformly distributed throughout the solder so that it has very stable strengthening effect even after aging. Here's some reliability data on SN100CV versus SN100C, its precursor, and SAC305. SN100C are the blue circles on the left. The green diamonds in the center are SN100CV, and then SAC305 are the red squares on the right. So when initially soldered, SAC305 lasts longer in this test. It had higher reliability. But then after aging these test boards 4,200 hours at 125C, the curves shifted position. Now SN100CV, the green diamonds, had the longest life or were the highest reliability after aging. Here's some data on an LGA 208 component that went through cycling at -40 to 125C. We've got SAC305 versus Inalot versus SN100CV in this data. And this was run on both OSP and ENIG surface finishes. So you can see that in this case, SN100CV on the right actually had a longer life than Inalot and SAC305 for this particular component in this test. Here's similar data for a BGA 360 that was cycled at a different temperature range, 0 to 100C. The blue bar is as soldered and the red bar was aged 6 weeks at 125C. Again, the characteristic life for SAC305 drops off as it does a little for SN100CV, but the overall life for SN100CV was much better than SAC305 in this test. Here's a summary of failure modes for those alloys that were studied in that work. I'm just going to cruise through this pretty quickly. So violet was tested, which is a proprietary alloy that's being evaluated for reliability purposes. It tended to fail at the interfacial and IMC layers. So it failed between the component and the solder joint and between the board pad and the solder joint. Inalot and another automotive alloy tended to have interfacial IMC failures as well as pad cratering. So Inalot and the other auto alloy were pretty strong alloys, almost too stiff. And so during thermal cycle testing, they tend to rip the pad right off the board. And that's not desirable. Or interfacial IMC failure is also not desirable. SN100CV, on the other hand, in this test tended to fail in the bulk solder, which is a more desirable failure mode. And theoretically, in the field, you could actually repair a failure in the bulk solder if you could resolder the solder joint. Whereas if you have an IMC failure or a pad cratering failure, it's very difficult to rework that. And so that wouldn't be repairable in the field necessarily. Here's another alloy called LFC2, which is a high reliability alloy designed for automotive industry. And this is a performance metric on the y-axis and then cycling on the x-axis out to 2000 cycles for a resistor. That's an 0805 size. So LFC2 is the blue bar at the top, and that maintained its performance even over 2000 cycles. SN100CV lost some performance over that period, and SAC305 lost even more performance. So it deteriorated much faster with thermal cycling. Here's cross sections after 2000 cycles of the solder joints on those components. You can see LFC2 on the left has very little cracking. It looks very clean. It looks like the solder joint's pretty well intact. In the center is SAC305. SAC305 has potential pretty good cracking going on there, and potentially those cracks would meet in the center somewhere and probably lift that component right off the circuit board. And then SN100CV on the right shows kind of cracking behavior in between those two, just like the performance metric showed on the last slide. And that's what the cross section is showing us. Here's a drop shock test for LFC2 being compared to SAC305 and also SN100CV. Here's the data for drops to failure. SAC305, which is also called SN97C, had 99 drops to failure in this test. SN100CV had about 50% higher life there, 145 drops to failure. And then LFC2 almost doubled the performance of the SAC305 with 184 drops to failure. So they're definitely more impact resistant than SAC305. Here's cross-sectional pictures of the failure modes. So LFC2 tended to fail in the solder bulk, and then SAC305 tended to fail along the intermetallic layer, as you can see here in the cross-section. Here's some vibration test data on 3 different alloys. LFC2 is the blue circles on the right, and then you got SAC305 as the golden triangle, and alloy A is an automotive alloy. Inalot is that alloy actually, and those are the red diamonds. In this particular test, LFC2 outperformed both SAC305 and Inalot in this vibration test. Here's cross sections of where the cracks propagated in that test. LFC2 had cracking through the bulk solder mainly. SAC305 also cracked through the bulk solder in this test, whereas alloy A was cracking through the IMC layer, which Inalot is kind of known for, at least in the data that we have shown so far. So LFC2 definitely showed the highest reliability in this test. Here's some properties of the 3 alloys I've been talking about. SAC305 versus SN100CV versus LFC2. The big difference here is you've got a difference in melting ranges. So SAC305 on this data chart melts between 218 and 219, or commonly I see it written as 217 to 220 C, but it's right there in that range. SN100CV melts a little higher than that, 221 to 225, although it reflows in a similar profile to SAC305. And then LFC2 actually has a slightly lower melting point. It melts between 208 and 213, So roughly 5 degrees lower than SAC 305. So you can actually run your oven a little bit cooler with LFC2. And then the compositions are shown there and relative costs. So the big hitter on this slide is if we assume SAC 305 to be the baseline cost and we assign 100% cost to that, SM100CV, just based on the materials alone, is about 70% less costly than SAC 305, or at least it was at the time I created this presentation. And that's because it does not contain silver, but it does have some added bismuth, which increases the cost a little bit. But the fact that SM100CV has a lower cost than SAC 305 makes it attractive to folks who are trying to save money. LFC2, on the other hand, because it's a high reliability alloy, it is a tin, silver, bismuth, copper mixture. It has a higher cost than both of these. So it's approximately 30% higher in terms of raw material cost than SAC 305. Here's a little bit of data on the profile used for TempSave B37. So B37 is designed as a low melting alloy that outperforms traditional tin bismuth 58 and tin bismuth 57 with silver. The composition is proprietary, but it's based on tin with 37% bismuth and some additives. The melting range is 139 to 174 C. So it actually melts approximately 10 degrees cooler than tin lead solder. So that makes it attractive for folks who have thermal challenges on their circuit boards or components that are sensitive to heat. I've also seen this used successfully by a customer who was running SAC 305 as their main alloy. And they were building controller boards for LED lighting. And on one side of the board, they had pretty heavy, large, dense components, and on the other, much lighter components. So they were assembling the heavy component side first with SAC 305, and then when they ran side 2, they were running it with TempSave B37, because when they ran side 2 with SAC 305, the heavy component side was facing down in the oven, and some of the components were actually separating and falling off the board. And so by switching to TempSave B37 for their second side, they were able to reduce the profile significantly and avoid melting those SAC 305 solder joints that were on side 1, which was facing down in the oven. So that's one advantage of running these low temp solders. Well, that brings us to a summary of everything I've talked about. So AmpWash solder paste was designed to have wide performance windows in both print and reflow. It definitely has excellent performance in those areas and even exceptional voiding performance. We would call this an ultra low voiding solder paste. It definitely has the ability to give high reliability solder joints if you choose the higher reliability alloys that I've been talking about. And it can amplify your process window. So that's all I have to say about AmpWash solder paste today. Now we'd be happy to take any questions.